Hello and welcome to this revision session for AQA A-Level Physics. So today's revision session we're going to look at Physics Paper 3 and the practical part of this particular paper. So in this revision session we're going to look at how to answer examination questions on A-Level Physics Paper 3 for AQA focused on the practical skills. So if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and then understand what topics you need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, firstly, when completing your work in this revision session, divide your piece of paper into two sections, with the left hand side larger than the right hand side. And on this section, write down your working out into the questions in this revision session. Then when you're doing this, make sure you're writing in full sentences and show your full working out. Now in the right hand side, write down any piece of information which you find useful, any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes, the textbooks to learn the key ideas of the course. This could include making mind maps or writing out notes yourself. The second step is to test yourself. So use Caboodle, use Seneca, use the student knowledge checker to quickly test your own knowledge, and you may wish to do this from cue cards. Then the third step is to practice exam style questions. So use the exam prep books, the homework books, supervised study books, the additional workbooks to answer exam questions and mark your own work. Now you may wish to download your own exam papers to do this. So these steps of learn the key facts, then testing yourself, then practicing exam style questions will help when you revise for your A-Level Physics. So let's now have a look at practicing some practical skills questions for Paper 3 in AQA A-Level Physics. The first question says, Figure 5 shows the apparatus used to investigate the bending of a beam. The beam is placed horizontally on rigid supports. Distance L between the supports is 80 centimeters. A traveller microscope is positioned above the midpoint of the beam and focused on the upper surface. Figure 6 shows an enlarged view of both parts of the vernier scale. The smallest division on the fixed part of the scale is 1 millimeter. What is the value of the vernier reading R0 in millimeters? So pause the video now, then unpause the video when you want to go through your answer. Right, it's an important skill that you can be able to read the vernier scale. Now it's important to note that when you are reading your vernier scale, the first value that you take is just going to be the whole number value, and that's going to come as it's the value, it's the last value before the zero starts. So you'll see on this particular scale that it goes 35, 36, 37, then there's 0, then there's 38. So we can tell straight away that it's going to be 37. Now the next thing is it's going to be 0.8, because then what you do is to find the next point, the decimal place on your vernier scale, is to then see when the points are aligned between the vernier scale and the normal scale. So you'll see that 1, 2, 3, 4, 5, 6 and 7 aren't aligned with the scale, but 8 is, so it's 37.8. The next question says, Figure 7 shows the beam bending when a hanger of mass 0.050 kilograms is suspended from the midpoint. The microscope is refocused on the upper surface and the new vernier reading R is recorded. The vertical deflection S of the beam is equal to R minus R0. The total mass suspended from the beam is increased in steps of 0.050 kilograms, and a value of S is recorded for each M up to a value of M equals 0.40 kilograms. Further values of S are then recorded as M is decreased to 0.050 kilogram steps until M is 0. Student A performs the experiment and observes that the value of S during unloading are sometimes different from the corresponding values of loading. State the type of error that causes the difference student A observes. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this type of question you've got to understand what type of error it's causing. Now there are two major categories of error you can think of, which is a systematic error, which is the same error on all results, or a random error, which is a different value for all particular readings. Now in this case you'll notice that the student sometimes gets different values, so therefore it isn't on every value. So because it's only sometimes, it has to be a random error, not a systematic one. The next question says, Student B performs the experiment using a thinner beam but with the same width and made from the same material as before. Discuss one possible advantage and one possible disadvantage of using the thinner beam. So pause the video now, then unpause the video when you want to go through your answer. Right, in this type of question, you've got to think about how it will affect all parts of your particular value. So the first advantage is if you use a thinner beam, you're going to be having larger values of extension being taken place, because it's a thinner value, so it'll be easier to extend or bend more. So therefore, we've got larger values of S, so the percentage uncertainty in the value is going to be reduced, because we're getting larger values with the same absolute uncertainty, so our percentage uncertainty goes down. But the disadvantage is undergoing so much extension, this relates back to your knowledge of materials, is that it's now going to undergo plastic deformation or inelastic deformation. So the graph will not be linear, it will be curved, or you could also say that the beam may break, or the actual beam may slip off the supports. And finally, you could also say that if you've got a thinner beam, you can't use as many masses, because if you then have a same range of mass for the thinner beam, it might snap before then. So they're all possible errors that could take place. The next question says, figure 8 shows the best line fit produced by the data collected by student A. It can be shown that S equals nm over E, where E is the young modulus of the material and n is a constant. So deduce in seconds to the -2 the order of magnitude n, where E equals the young modulus 1.14 gigapascals. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first thing to note is with the young modulus, it is actually going to be 1.14 times 10 to the 9, because it's in gigapascals. So that's very important that we know that. Now we're trying to work out what S is, so and we're going to do then S to the -2. So how can we then work it through? Well, we can rearrange it and make n the subject. So we can say n is equal to SE over m. And then what we can therefore do is, if we know S is equal to nm over E, well, therefore we can calculate the value by looking at the different values that we can get. So we can say n is equal to SE over m. So we can therefore work it through by saying, well, S over m is going to be the gradient. So because we know from the graph, well, gradient is y over x, so we can work out what the gradient is going to be, pop in the numbers, and therefore we can work out what it is, because we know what E is as well. So we should hopefully get the correct answer. So it should be in the order of magnitude 10 to the 8. Now, the next question says, figure 9 shows that log 10s varies linearly with log 10l. State what this shows mathematically about the relationship between s and l. Don't do a calculation. Then deduce using figure 9 the value of s when l equals 80 centimeters. Then determine m using figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So the first question is looking at what's the relation between S and L, but it's going to be log S and log L that they vary linearly with. So therefore what we can say is that S and L are linked by the power law, because what we can say is that when you've got a logarithm involved and you're getting a linear relationship, that they must be linked by an actual power. So you could say S is directly proportional to L to the power of something. So for example, it could be S is directly proportional to log to the power 3. Or you could say S is equal to KL to the power 3. So you can work it through like so. Now then, using figure 9, what the value of S is when L equals 80 degrees. So what you can therefore, 80 centimeters, sorry. So what you can do is, because we know we've got log L, so what we can do is we can work out what the value of log L is when we can work this through. So what we can do is you can work out what log L is, so work out log L is going to be equal to minus 0.097. So we can work that through, as it's going to be the y-intercept, so you can work it through like that. And at that point we can work it out, sorry, not the y-intercept, my apologies. Okay, it's going to be the value on your particular graph there, so it's going to be minus 0.097. So therefore what you can therefore do is then use figure 9 here to work out what S is going to be, because you can work it across and then you can link it in as such. So therefore you can get your value to be about 3.1 times 10 to the minus 2. Be careful that we're using log 10 as the base, not a natural log. So it's log 10, otherwise you won't get the right answer. Now finally, how do you work out m? Well, what you can do is, in the previous question you got the equation for m, so you can work it all through, because you've got your different values of L, S and E, so you can work it all through to work out what m is. So it's going to be the value you just worked out before times by the gradient, which is going to be log S over log L. Now the next question says an analog voltmeter has a resistance which is much less than that of a modern digital voltmeter. The analog meter can be damaged if the full scale reading is exceeded. Figure 6 shows a dual range analog voltmeter with a zero error. The voltmeter is set to a more sensitive range and then used in the circuit. What is the potential difference between the terminals of the voltmeter when a full scale reading is indicated? So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this particular question? Well, you got to think in this particular question, you're looking at what the biggest value is going to be, okay, and working it through like so. So what's the potential difference between the terminals when the full scale reading is indicated? So you're going to have to work out what the biggest possible value is when you're working this through. So we're using the more sensitive range that's used in the circuit, so therefore we're going to use the lower one, because as a result you can see that it's going to be climbing upwards like that. And then it also says that the reading can be damaged when the full scale reading is exceeded, so therefore our value is going to be 2.7 because the biggest value you can get to is 3, but you want to be going to the one before that, so therefore we're looking at 2.7. Now the next question says explain the use of the mirror when reading the meter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question was all about experimental technique. So you've got to think, why do you need the mirror there in terms of you're using an analog scale? So you're looking at a actual measuring point on a scale. So you move the position until the needle is aligned with the reflection in the mirror. So something like that. So you're using it, so you move the position until the needle is aligned with the reflection. So we therefore know we're looking at it dead on. Now why do we want to look at it dead on? We want to look at it dead on to reduce the effect of parallax error, because parallax error is when you don't read the scale directly from above, you're looking at an angle. Well, it can't be at an angle if the reflection is in line from the mirror with the actual needle pointer. The next question says, this question is about the determination of the Young modulus of a metal wire. In an experiment, two vertical wires P and Q are suspended from a fixed support. The fixed part of the vernier scale is attached to P and the moving part of the scale is attached to Q. The divisions on the fixed part of the scale are in millimeters and an empty mass hanger is attached to Q and the scale is set to 0. A load is added to the mass hanger so that the extension of Q can be measured as shown in figure 1. The reading on the vernier scale can be used to determine the extension of Q. Then figure 2 shows how the extension varies with M, the mass is added to the hanger, determine the mass added to the hanger shown in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first one, we're trying to use figure 1 here to work out what our extension is. So we're going to have to use our vernier scale measurement, our vernier scale here to work out the different values between the value on the left and the value on the right hand side. So when we use our vernier scale on the left hand side, we can see quite clearly that when we're working this through, we're going to get a value out, okay, at the Z. Well, if you look on it, you're going to be looking at 0. If we look at the alignment of their 0.1 between the two scales there, and then on the extension, the second one, we're looking at the value to be 2.8. So at that point, because 2.8 aligns on the right hand side and 0.1 aligns on the left hand side, we will do 2.8 minus 2.1 minus 0.1, and so therefore the extension is the difference, so it's 2.7. It's really important you can read vernier scales correctly. Now the next one, determine the mass hanger shown in figure 1. So how can we work this one through? Well, we can work out our mass to be 5.8. Why is it 5.8? Well, because we've just worked out what the extension is going to be. We've worked out our extension is 2.7. So therefore we go up on our graph to 2.7 on the y-axis, read across, read down, and we get our x-axis value to be 5.8 kilograms. The next question says a student uses digital vernier calipers to measure the diameter of Q. She places Q between the jaws of the calipers and records the reading indicated. Without pressing the 0 button, she removes Q and closes the jaws. The views of the calipers before and after she closes the jaws are shown in figure 3. Calculate the true diameter of Q. So pause the video now, then unpause the video when you want to go through your answer. Right, so what do we do here? We've got to be able to work out what our diameter is going to be when measured, but we've obviously got a zero error because we're reading minus 0.07 when the jaws of the caliper are closed. So they've got a zero error of minus 0.07. So we should always minus the zero error from our particular reading, which is 0.44. So when we minus 0.7, we're adding 0.07, so the value is 0.51 millimeters. The next question says, the student repeats her experiment using a wire of the same original length and metal but a smaller diameter. Discuss two ways this may affect the percentage uncertainty in her result for the Young modulus. So pause the video now, then unpause the video when you want to go through your answer. Right, in these types of questions it's always very important you think of all the factors in the particular equation and see how changing the diameter will affect those values in your Young modulus. So the first thing to note is that when you use a smaller diameter you get a larger extension. So this will reduce the percentage uncertainty in the extension, so therefore reduce the percentage uncertainty in the Young modulus. But using a smaller diameter will increase the uncertainty in the cross-sectional area part of the Young modulus measurement, because we know area is pi r squared and diameter is r over 2, so therefore it will increase the percentage uncertainty. Now in addition to that you'll have another factor. It's that when you've got a lower diameter, therefore the wire will reach its limited proportionality a lot faster, or be more likely to, with the masses that you're going to do. So therefore you won't be able to get high enough range of readings for your mass, which will be important when you add it in, because you can say when you're working out your Young modulus you need your force, which links into your mass, because F is going to equal mg in this instance. So therefore it'll increase the percentage uncertainty for that value, so overall it'll increase the percentage uncertainty for your Young modulus. Always consider all the factors in the equation for a particular value. The next question says, a student decides to carry out a similar experiment. The student thinks the meter in figure 7 could be used as a microvoltmeter to measure E, the EMF. When this meter indicates a maximum reading and the needle points to the right hand side of the scale, the full scale deflection, the current in the meter is 100 microamps. The meter has a resistance of 1000 ohms. Calculate the full scale deflection of this meter when used as a microvoltmeter. Then the scale on the meter has 50 divisions between 0 and the full scale deflection. Discuss why this meter is not suitable for carrying out the experiment. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how to work out the full scale deflection? Well, what we've got is we know the full scale deflection is going to be when you get to the end of the scale, which is going to be at 100 microamps, and we know that the resistance is 1000 ohms. So what we can therefore do is we can say that, well, V equals IR, we know that equation, and therefore we know that it's going to be 100 microamps times by 1000 ohms. So therefore we get 10 to the 5 microvolts. Okay, and remember we want to work in microvolts because that's what the unit is given in the question. Now, will this be a particular suitable scale? Well, no, it's not, because the resolution is not going to be satisfactory, because the largest PD will be less than 1500 microvolts. So therefore you're only using about 1.5% of the range, so therefore you won't be able to really use it very sensitively, and it won't get a very good result. The next question says, this question is about an experiment to determine the internal resistance of a power supply. The student is given a circuit and the 4 resistors of known resistance in figure 1. The student can change the external resistance R of the circuit between terminals X and Y. This is done by connecting different combinations of 2 resistors in series or in parallel between X and Y. This method can produce 12 different values for R. Calculate the largest value of R that the student can be obtained using 2 resistors. Then calculate the smallest value of R that the student can be obtained using 2 resistors. So pause the video now, then unpause the video when you want to go through your answer. Right, this question is relevant by the fact of you need to know the circuit laws, and that is when you add resistors in series the value goes up, but when you add resistors in parallel it goes down, because 1 over RT equals 1 over R1 plus 1 over R2. So to find the largest value resistance that from 2 resistors, you add the 2 biggest ones. You can see in series you just add the 2 values and you get 15 ohms. Now to find the smallest one, what you will do is you will add 2 values but in parallel. So what you you will do is you need to select the two smallest values, and you still then place them in parallel, because when you add them in parallel, it decreases the resistance even more. So you get the two smallest values anyway, and then add them in parallel. So you say 1 over R total equals 1 over 2.2 plus 1 over 3.9. You work it through and you get 1.4 ohms. The next question says, figure 2 shows one particular combination and arrangement of two resistors that the student could use. When S is closed, the voltmeter reading V is 1.14 volts. Explain why V is less than 1.62 when S is closed. So pause the video now, then unpause the video when you want to go through your answer. Right, once again, this is linked to you understanding the idea of internal resistance, because when the switch is closed, you'll notice that the circuit then is complete, so then current can flow. At that point, the voltage will drop because there will be lost volts due to internal resistance. So as the EMF is then produces a PD to flow through the circuit, you're then going to get your internal resistance, you're going to get lost volts, so therefore the value will not be as big as it would be for the EMF. The next question says, figure 4 shows a different method for varying R resistance described to the previous question. The four resistors are connected in a loop with sockets A, B, C and D at each junction. Two leads are used to connect the resistor loop to X and Y. Discuss whether this method is an improvement over the method described in the previous question. In your answer, refer to the number of different values that can be obtained for R. So pause the video now, then unpause the video and you'll want to go through your answer. Right, well in this question it indicated to you, okay, that we need to work out how many values we can determine. Now in the figure 1 method it said you could get 12 different values. Now in this particular method you can only get 6 values. So you can note here, okay, that you can only get 6 possible combinations of getting the resistors in there by looking at the different circuits. So therefore when you notice that you can only get 6 values for R by this method, it won't be as good because figure 1 can get 12 different values. So because you can get more values, you're going to get a better experimental results, so it's important that that is recognised as the reason why figure 1 method is better. So I hope you've enjoyed this particular revision session and you've learned in this revision session. Hopefully if you've learned this revision session you can answer A-level physics paper 3 examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for paper 3 in AQA A-level physics. Thank you very much for watching this revision session and have a lovely day.